Hello and welcome. In this video, we're going to take a look at the solutions to waves practice assignment. Please remember to pause or rewind the video. Let's begin. Number one, what is a wave? A wave is some means of transferring energy. Now, a mechanical wave is a disturbance of a substance or a medium to transfer energy. A light wave is caused by nuclear fusion, and we'll get into the difference as the unit develops. So a wave is a transference or a transferring of energy. What is the difference between a longitudinal wave and a transverse wave? Transverse waves vibrate perpendicular to wave motion. An example of this would be a light wave, a wave of light. Light is transverse. Okay. By contrast, longitudinal waves vibrate parallel to wave motion. A sound wave is an example of this. Number three, for the wave below, find the following. Well, we need to find the number of cycles, the wavelength, the frequency, the period, the amplitude, and the wave speed. Let's begin. First, you'll notice that there are 1, 2, 3.5 cycles. Okay, so we're going to start off right in the beginning here, part A. There are 3.5 cycles. Okay, now part B, we can figure out the wavelength by taking the total length divided by the number of cycles. Now, the total length is 20 meters. So we can take the 20-meter oscillator, divide that by 3.5 cycles. That in your calculator. You get roughly about 5.7 meters for each wave. Part C, frequency. Well, the frequency can be found by taking the number of cycles divided by the measure of time. So there are 3.5 cycles. And if we divide that by 10 seconds, we're going to get the number of cycles per second, or the frequency, 0.35 cycles per second, or 0.35 hertz. Part D. Well, the period can be found by taking the inverse of the frequency. So the inverse, 0.35 is the frequency, 0.35 inverse roughly about 2.85 seconds. Part E, the amplitude. Now the amplitude is this distance here. It's the distance from the equilibrium middle to the highest or lowest point. And we can get that by taking the height. Now the total height of the wave is the high to low distance, which is in this case 12 meters. If we take that and divide it by 2, we'll have the amplitude. The amplitude in this case would be 6 meters. And then finally, the wave speed, part F, can be calculated by going frequency times wavelength. So we're going to go 0.35 times 5.7, and we get roughly about 1.995 meters per second, or roughly 2 meters per second. Either one would be fine. For number 4, similar problem to number 3. To do the number of cycles, we're given, that's 1 cycle right there, 2, 3, 4, 5, 6, 7, 8 complete cycles. So for part A, there are 8 cycles shown in the problem. Part B, the wavelength again is found by taking the total length divided by the number of cycles. The total length in this case is 4 meters. So 4 meters divided by 8 cycles would be a half a cycle, half a meter per cycle, or just half a meter. Part C, the frequency is found by taking the number of cycles per unit time, total amount of cycles by the total amount of time, 8 cycles, divided by, it takes half a second for this wave to travel. Well, 8 over a half would be 16 cycles in 1 second, or 16 hertz. Part D, we're looking for the period. Well, the period is the inverse of the frequency, so 1 over 16 is 16 inverse. Make sure you practice putting that in your calculator. 16 inverse is about 0.0625 seconds. Make sure you can do that yourself. Part E. Well, the amplitude is the distance from the middle to the highest or lowest point, which you can see is clearly on the picture here, of 1.5 meters. And letter F, we're looking for the speed of the wave, which is going to be frequency times wavelength. And we're going to go 16 hertz. And we're going to divide that by 0.5 meters of wavelength, which means the wave is traveling at 8 meters per second. Number 5. Now for number 5, it's asking, how does increasing the frequency of a light wave affect each of the following? So let's take a look at our light in terms of the colors and the information about light. So first, let's break light down into the respective colors. Okay, you have red, orange, yellow, green, blue, and violet. Okay, and what we will learn how this works is that red actually has larger wavelengths, violet has smaller wavelengths. So the wavelength is decreasing. The wavelength is decreasing as we go from red to violet. Now, since V equals frequency times wavelength and the speed of light is constant, what that means is a decreasing wavelength balances an increasing frequency. So that means longer, larger wavelengths are going to have much smaller frequencies, which means smaller wavelengths are going to have much larger frequencies. Also corresponds to energy as well. Small frequencies correspond to smaller energy, capital E. Larger frequency corresponds to larger energy. Okay, so let's take a look what we have here. Red corresponds to longer wavelengths, smaller frequencies, smaller energy, or less energy. Violet, blue-violet side of the color spectrum corresponds to smaller wavelengths, which represent larger frequencies and larger energy. Okay, so how does increasing the frequency of light, how does that affect any of these? Okay, well, what do we know? Increasing the frequency decreases the wavelength. So the wavelength would decrease. Okay, the period. Now remember, the period is the inverse of the frequency, right? So increasing the frequency would decrease the period. So the period would get smaller. The speed. How does increasing the frequency? Increasing the frequency means you're going from a redder color to a more bluish violet color, right? So what is increasing the frequency going to do with the speed? Well, the speed remains constant. Okay. Amplitude relates to the intensity of the light, which will remain constant. It's not affected by frequency. All right. Now the color, when we increase the frequency, the color is going to shift from a reddish color to a more blue-violet color. And then finally, brightness. Well, brightness relates to the intensity. Okay, so kind of like amplitude. Amplitude relates to intensity. So the brightness relates to the intensity of the light. Well, the frequency, changing the frequency doesn't change the intensity. They're independent of each other. So the intensity, excuse me, or the brightness will remain constant as well. Okay, so increasing the frequency would decrease the wavelength, decrease the period. Speed remains constant. Intensity, thus the amplitude and the brightness remain constant, and the color shifts towards blue-violet. How about decreasing the wavelength of a sound wave? Well, again, remember, velocity is equal to frequency times wavelength. So the speed, I'm going to start off with letter C. The speed remains constant. The speed of a sound wave remains constant. Why? Because a sound wave is based upon the temperature through which the sound wave is traveling through, the temperature of the medium. So like air temperature or water temperature, whatever the sound wave is passing through, it's completely based upon the temperature of that medium. And if the temperature is not really changing, the speed of that sound wave is not going to change. So for all intents and purposes, the speed remains constant. So what does that mean? If this is constant, that means a decreasing wavelength corresponds to an increase in frequency. So frequency would increase. Okay, and again, period is the inverse of the frequency. So if frequency gets bigger, period has to decrease, right? It's going to get smaller. All right, amplitude. Well, amplitude again is based on intensity, as is loudness. Loudness refers to the intensity of the noise, both of which would remain constant. It really kind of refers to the same thing. Okay, the pitch matches the frequency, which we already said is increasing. So the pitch will be increasing as the frequency is increasing. Questions 7, 8, and 9 are referring to calculations involving the speed of light. So now we know that V is equal to frequency times wavelength. Okay, for a wave of light, V turns into C equals frequency times wavelength, where C is the speed of light, and the speed of light is a constant value of 3 times 10 to the 8 meters per second. So this value for V, which is going to become C now, is a constant value here, okay? So we have C for every one of these problems. Here we go. Now, something to consider about light, and we didn't address this above, so I'm going to address it now because this is often a point of confusion with a lot of students. There's actually 7 different forms of light. So I'm going to draw a line right here. And let's address these 7 different forms. So we have, to start off with, radio waves. Radio waves are one form of light. Then we have microwaves. Then we have infrared. Infrared is typically known as IR. Then we have the visible light. Well, the visible light would be the colors of your light spectrum, what you can actually see. So on the other side of infrared would be the color red. This is where our red, orange, yellow, green, blue, violet take place. On the other side of violet would be ultraviolet, typically known as UV. Okay. On the other side of ultraviolet would be X-rays. And then finally, gamma rays. So there are actually 7 different forms of light. 1, 2, 3, 4, 5, 6, 7. However, only one form of light do we actually see. The total of all these colors would represent white light. So white light, when split through a prism, like a raindrop or any other crystal, will refract and disperse into the colors of the rainbow: the red, orange, yellow, green, blue, violet. But in totality, they really represent the total of white light. What is the frequency of a wave of light with a wavelength 6 times 10 to the negative 7 meters? So there's our lambda. Right, we're looking for frequency. Okay, so C is equal to frequency times wavelength. We're going to solve for F by dividing by lambda, divide both sides by wavelength. So frequency is equal to C over lambda. Now remember, C, speed of light, is this constant value here, 3 times 10 to the 8 meters per second. So 3 times 10 to the 8 meters per second. Divide that by 6 times 10 to the negative 7 meters. Okay, throw that in your calculator. And we get 5 times 10 to the 14, and we're looking for frequency, so this would be hertz. Okay, now in the next question, we want to know what is the wavelength. We're looking for lambda, right? And we have a frequency of 7 times 10 to the 14, 6 times 10 to the 14. Okay, so same idea. If C equals frequency times wavelength this time, we're going to divide by frequency to get lambda, the wavelength, by itself. Okay, and we get lambda equals C over frequency. Remember, C is our constant speed of light, to 3 times 10 to the 8 meters per second, over our frequency of 6 times 10 to the 14 hertz. Go ahead and plug that in your calculator. Okay, and we get a very small number, about 0.000005. So that would be 1, 2, 3, 4, 5, 6, 7, or 5 times 10 to the negative 7 meters. Okay. What is the speed of a radio wave of frequency 110 megahertz? Well, this is kind of a trick question because it's not really a calculation. Just remember, all forms of light that we see here all have a couple things in common. One, they can all travel through the empty vacuum of outer space. They don't need a medium to vibrate like a sound wave does. Two, they all travel at the same speed. So radio waves travel just as fast as X-rays do, just as fast as visible light or gamma rays. So how fast is a radio wave moving? 3 times 10 to the 8 meters per second. We're not doing a calculation here. This is a reminder that a radio wave is a form of light, and all light travels at the same speed. Number 10. What is the speed of a sound wave of frequency 550 hertz in air at STP? STP stands for standard temperature and pressure. Okay. Well, the average speed in these conditions, we're actually told right here, is 345 meters per second. So the speed at standard temperature and pressure, right, is approximately 345 meters per second. In other words, that is the generally accepted value of the speed of a sound wave. Now, standard temperature and pressure means room temperature, so about 70 degrees Fahrenheit, about 25 degrees Celsius. It means 1 atmosphere of pressure, right? Those are the standard conditions at which you would get that particular speed of a sound wave. Number 11, what is polarizing light? How do polarized sunglasses protect from glare? Okay, so in order to kind of see this, I'm going to go down to the bottom and draw a picture of this. So when light comes from the sun, light from the sun vibrates in all directions. Okay, it vibrates in all directions. Let me show you what I mean. If we take a look at this image, we can see that there are 2 transverse waves perpendicular to each other. Okay, This animation shows an electromagnetic wave. When we say electromagnetic, we mean a wave of light. So all waves of light, whether they're radio waves, microwaves, infrared, any color of the spectrum, ultraviolet, X-rays, or gamma rays, any form of light is going to resemble this, okay, where we have transverse waves oscillating in different directions. So we simplified it to suggest a red direction. Now the red direction is the electric field direction. The blue direction is the magnetic field direction. Notice that as the red direction oscillates up and down, it creates a blue direction. So the electric field, the changing electric field generates a magnetic field. And the changing magnetic field generates more red, which is electric field. This is what's called a self-propagating wave. What that means is once the wave goes, the electric field keeps the magnetic field going, the magnetic field keeps the electric field going. The wave just keeps going without any vibrating medium. This is why waves of light, they can pass through air, but they don't require air. They don't require water. You don't require a medium to vibrate in order for waves of light to pass through. All right. This, what we're looking at, is known as unpolarized light. Okay? This is polarized light. Polarized light is referring to a wave that is in direction. So this is unpolarized because it's vibrating in all sorts of directions. Okay? If we were to focus on polarizing the light in, let's say, only the red direction or the blue direction, we would need a filter. Now let's take a look at what that might resemble. Okay, now let's focus on how do sunglasses protect from glare. Let's take a look. What we have, I'm going to draw a pair of sunglasses here just so you can kind of see. So a pair of sunglasses. Now the way sunglasses work, I'm going to zoom in on this. Sunglasses actually have across the lens a filter, a polarizer. And what the polarizer does, it's made of a bunch of thousands of these tiny little vertical slits, almost like picket fences, okay? And let's say we have water, okay, or a shiny car, or a piece of metal, or something like that. What happens is the rays from the sun, they come out well, they're going to be transverse in two directions. They're going to be transverse horizontally and vertically. You have what is called unpolarized light. Now, once it reaches the surface of the water, majority, not all of it, you're going to reflect light from the surface of the water or the surface of the hood of a car or anything like that. And what's going to happen is most of the reflected light is going to be horizontally polarized light. Okay, now some of it will be vertically polarized light, but most of it's be horizontal. Notice the filters in the sunglasses are vertical slits. What that means is the vertical polarizers in the lenses of sunglasses help to filter the glare. Now, what is the glare? The glare would be horizontally polarized light. So what's reflecting off of a water surface or the hood of a car in front of you when you're driving? Horizontally polarized light. Well, horizontally polarized light is not going to fit through vertical filters. So a lot of it is darkened out, which is why when we wear sunglasses, a lot of the light is eliminated and darkened. You do see a shade of the light because some of the vertical polarized light has still bounced off of the surface here. It's just not much of it is there. Hence, it's very dim and dark through sunglasses. So polarization, polarized light is light vibrating in only one direction. Number 12. Select answer A or B for each of the following. Wave A is over here. Wave B is over here. All right. Now, part A, which one has a higher frequency? Well, this one repeats more often. Or we could say more rapidly repeating. That's one way to look at it. Or we could say smaller wavelength, right? A higher frequency goes with a smaller wavelength. They're inverses of each other. Okay, which one has a smaller wavelength? Well, that would be A. Right, wave A has smaller. Which one has the longer wavelength? Well, that would be the one with the lower frequency. That'd be B. Which one has the longer period? The longer period, remember guys, period is the inverse of frequency, right? So longer period is the one with the lower frequency. Okay, the one with the lower frequency, which would again be B. Okay, higher amplitude, that's going to be the taller wave. That's clearly going to be A. A is much taller from the middle. The redder color. Now remember, according to our spectrum, Roy G. Biv, red, orange, yellow, green, blue, violet. Well, redder colors have larger wavelengths, smaller frequencies. Okay, the wavelength is going to decrease. The frequency is going to increase. Okay, so a redder color is one that has a smaller frequency or a larger wavelength. That would be smaller frequency or larger wavelength. That would be wave B. Okay, higher pitched sound. Higher pitch goes with the one when it is a larger frequency. Larger frequency would be A. It's repeating more often than A. Brighter light. Brighter light goes with the one that has the greater amplitude. Because brightness corresponds to intensity, which matches the amplitude of the wave. So greater amplitude would be A. And finally, quieter sound. Quieter sound goes with the lower amplitude. So quiet goes with the intensity of the sound wave, which also relates to amplitude. So we're looking for the wave with the lower amplitude, the quieter noise, quieter sound. That would be B. Okay, 13. Identify each of the waves below as transverse or longitudinal. Okay, so B is transverse. Because each particle on the wave is vibrating perpendicular to wave motion. This is longitudinal. Wave A is longitudinal because you can see it's vibrating left and right parallel to wave motion. Okay, number 14. A star gives off electromagnetic radiation, that means light, with a wavelength of 4 times 10 to the negative 7 meters. The light detected from Earth is about 3 times 10 to the negative 7. What do you know about the motion of the star relative to Earth? Explain your answer. Well, ladies and gentlemen, this is a Doppler effect problem. Doppler effect does not just relate to sound, as we demonstrated in class. It relates to light as well. Here's what we know about that. The wavelength was detected to be smaller. So if we take our equation, c, the speed of light, which by the way is constant, and that's equal to frequency times wavelength. So if this is constant, what that means is your wavelength was detected as smaller, which means your frequency would have to be bigger. Well, a larger frequency detected frequency would mean the star is approaching the Earth. So we demonstrated in class that a sound going from a higher pitch to a lower pitch would show you an object approaching you and then going away from you, right? But that's based on the sound of the frequencies we perceive getting higher than lower. Well, we're doing the same thing, but the idea is this frequency is now detected in terms of the wavelengths or the colors. So if something is shifting towards a violet color, a bluish violet color, then that means the frequency is getting bigger and it means the star is getting closer. If the star were shifting more towards a reddish color, okay, that means that would be shifting towards a lower frequency and means that star would be getting farther away from Earth. So we can apply Doppler effect to waves of light as well as sound. Number 15, bats use sonar to see. He sends out a sound wave which reflects off objects and back to the bat. Based on how long it took for the wave to return, the bat can determine the distance of the object. So the bat sends out a sound wave at STP. Now remember, STP means the speed of the sound wave is about 345 meters per second. So I'm going to help you out with that. It reflects off a mosquito, which is really tiny, and back in about 0.02 seconds. How far away is the mosquito? Here we go, part A. Part A, we're going to do a simple velocity equals distance divided by time. If we multiply both sides by time, that means distance is equal to speed times time. So how far away is the mosquito? Well, the sound wave is traveling 345 meters per second, and now it gets to the mosquito and back in 0.02 seconds. That means it gets to the mosquito in 0.01 seconds, half of that time. Multiply that together, and the mosquito is about 3.45 meters away. Not too far away. Okay. Then we can establish if the sound wave bounces back at a higher frequency, what does that mean about the relative motion in a bat and the mosquito? Well, if it's bouncing back at a higher frequency, what that means is the bat and mosquito are getting closer to one another. This is a Doppler effect example. And finally, question 16. Answer A or B for each of the following. It's very similar to what we did in number 12. Wave A is over here, wave B is down here. Okay, now if I count these up, these waves are traveling in the same amount of time. I'm just going to count them up real quick. I have 1, 2, 3, 4, 5, 6, a little more than a half, 6 3/4, I guess, of a cycle. Over here, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 3/4. So we have almost twice the number of waves in B than we do in A. Okay, so which one has the higher frequency? Again, the higher frequency is the one that repeats more often. Repeats more often. In the same amount of time. That would be wave B. Okay, which one has the longer wavelength? The one with the longer wavelength is the one with the smaller frequency. That would be wave A. The longer period, now period is the inverse of frequency, right? So longer period means the one with the smaller frequency. Again, wave A. Okay, higher amplitude. Well, we're looking for the taller wave. That would be wave A. Redder color. Redder color means smaller frequency. Smaller frequency corresponds to A. Repeats left on. Higher pitch goes with the greater frequency. Should be wave B. Okay, brighter light and quieter sound go with amplitude. So brighter light would be the one with the greater amplitude. All right, and the quieter sound would be the one with the lower amplitude. The greater amplitude would obviously be A, and the lower amplitude would obviously be